Ideas have been building video pipeline software for specifically live high resilience systems for about the last 7-8 years. Before that, Adrian and I were in financial services and retail systems and such like. So we've got a lot of experience of building highly resilient systems that sit historically in big data centers, but nowadays in the cloud, which frankly are just someone else's big data centers. And what we're going to do in the next 25 minutes is talk a bit about what high availability is and how you go about putting together systems that you can rely on, specifically on live video. So not so much VOD, that's frankly a bit easier, but live is harder. Live you only get to do once.
I'm probably going to let Steve, given we've got a fairly short amount of time, I'm probably going to let Steve drive, and then I will kind of chip in annoyingly.
Chip in whenever I forget stuff or get it wrong. So what does high availability even mean? Everyone talks about SLAs and people talk about 5 nines and such like. We thought it'd be interesting to just throw some numbers up as to what they were. To get people to think a little bit about what these numbers mean, because it's easy to say 9 nines SLA, but what the heck does that mean? Well, it means you're up for 99.999% of the time, but what does that even mean? Is that over the course of a year, or over the course of a day, or over the course of a 100-meter final? The answer is very different. So you need to know how you're being measured, and you need to know what the implications are if you miss. If you've got a very high SLA and you're doing a sporting event and it's a wet afternoon with nothing happening and you go down, no one's probably going to care, even though technically you breached your SLA. If you go down in the middle of the 100 meters final, people are going to care a lot, even if you don't breach your SLA. So there's a lot of things about watching how to measure. So if you look at the numbers, 90% per year, that's easy. You can be down for, 36 days, walk in the park. So that's no one here is interested in that. Right at the other end of the scale, if you're at 9 nines and you're being measured on a daily basis, you can be down for 0.86 seconds a day. That's not very long to handle any sort of error. You really don't have much time to respond there. Relating that to the 100 meters final, if you were down for 99.999, if you were up for 99.999 in the final, you'd only lose a millimeter. That's okay. But the reality is that isn't going to be what happens. Let's say it's your daily outage, and let's say you can get back in time, 0.86 for seconds. You've still missed the guy crossing the line. That's a shame. So you really need to know what these numbers mean. You need to know how they apply to your customers and what your customers mean when they ask for these numbers.
You also need to kind of think a little bit about how it applies to your suppliers. So, for example, it's very common with traditional systems just to back-to-back your SLAs. That's, I've got a big old enterprise SLA, and I'm going to talk to posh providers who are going to give me enterprise SLAs, and someone like Amazon, AWS, they've upped their SLA in the last couple of years because it had changed since the last time I looked, and they'll give you a 4 nines SLA now, which is great. Now, they're actually very explicit about how they measure that. They measure that over the course of a month, which means that they can be down for 4 minutes, 38, whatever it is, seconds. And then if they go a second over that, they will give you EC2 credits to the tune of a second. So if they're down for your 100 meters final, they'll go, we're terribly sorry about that, here's 12 cents. And that's probably not a very useful, so it used to be when we were building banking systems, you would, here's a big SLA, and here's another big SLA, and here's another big SLA, and you kind of chain them all together, and you say, hence big SLA, just doesn't hold anymore.
Where does the downtime come from? There's 2 main areas of downtime. One is controllable downtime, the other is uncontrollable downtime. Controllable stuff is, as it says, stuff that you have control over. This is stuff you can schedule. This is stuff you can plan. This is all essential. This is essential housekeeping. You don't have a choice on any of this stuff. You have to do OS patches from time to time. You have to upgrade your software stacks. You are going to have hardware maintenance to do, whether it be upgrades or just refresh of things before they fail or whatever. You are going to have security patches that come in. Sometimes you'll have control over those. Where SLAs are concerned, even if you're on a high nines SLA, typically you can actually schedule stuff, especially in the context of a live system. It's very rare you have a live stream that's running for days or weeks or months on end. Anything for that length of time, typically there's going to be an ad break, or there's going to be somewhere where you're running off some VOD content and you've got time to take some bits of your system and do work to them. So controllable downtime, to a degree, you can ignore when it's coming to the numbers. You can manage that through mechanisms that won't impact your SLA, won't impact your customers. The other page is much more interesting. This is stuff you have no control over. This is where things just go wrong. This is where you have a bad day. Hardware fails, you have failures in your source ingest, you have failures going out to your CDNs. You might have attacks, DDoS attacks or something that you need to manage. You can have software failure, just bugs. The key with all of that is complexity is your enemy. The more complex you make your system, the more likely all of these become. Chain is as strong as its weakest link and all that. Now, a lot of people would say, well, don't you just do it properly? Don't you just write really good software and run it on really good networks and put it on really good hardware from really good manufacturers that design their systems very well? And certainly if you roll back many years, that was exactly what everybody did. You just spend a fortune, particularly on the software thing. You have huge QA teams, you go through big code review processes, you have bits of your department actively looking at formal languages and so on so they can prove that your system does what it says it does, except there's nothing that can prove that what you said it did is actually what the customer wants you to do. The whole thing's just a big stack and you can never prove the whole thing works. That doesn't stop people spending an awful lot of money trying to prove that it will, to make sure it never goes wrong. The reality is it is going to go wrong. It doesn't matter how hard you try, your system will go wrong. Stuff will break. Hope is not a good strategy for hitting an SLA. And just because it's worked fine for the last X years doesn't mean it's going to work fine tomorrow.
That's an incredibly common phrase that we hear. Well, someone will go, oh, well, we've had a system that's been up for a year without any downtime, therefore we have a 5 nines SLA. And it's, no, you don't. You have a sampling error, of unknown size is where you are right now. And in order to have some kind of confidence that your system does have, you're talking about, we're not talking about 99% availability, we're talking about big nines here, about hard stuff. And just saying it's worked for 2 years, I'm not interested. It's not, who cares? If it's gone wrong every day for 2 years, I'm really interested in that.
Absolutely, yeah. So we have one system that's been up with service availability of 7 years. We've never had a live support call. That's not because it's always worked for 7 years. It's absolutely gone wrong all the time. But it fixes itself.
His code went wrong all the time. Mine was fine.
He spent much more money writing his code. Mine was dirt cheap. How do you start hitting some of these numbers? What's the approach you can take? You can kind of ignore the sort of 99% and below. Most people in this room probably aren't interested in those numbers, and frankly, they're easy. You've got so much time to respond to stuff that you can just have a single box sat in your cupboard doing the job. And
I met an encoding vendor a year or so back, whose name should definitely remain nameless, who I sort of said, oh, so what do you do when an encoder fails? And he says, oh, what we do is we send an engineer into the room and they take the SDI cable out of that one and they put it into the replacement and they turn it back on again. And they called it orchestration by human being, which is kind of, Kubernetes is not, but whatever.
Yeah, it works, and if you can cope with that, that's a really good way to do it. At 99.9, your time's getting limited. Knowing what period your SLA is measured over starts becoming very interesting. If you're measured, let me hop backwards, where are we? Where's 99.9? If you're measured per day, frankly, it's still pretty easy. You've got 1.4 minutes. If your SLA is over the course of a month, and assuming you're not going wrong every single day, you've got 10 minutes to spare. So 99.9, if you're very organized and you plan what you're going to do, you can probably still get away with a fairly simplistic approach to delivering that sort of number. That's not particularly hard. Once you get up to 4 nines, it starts becoming out of the realms of human control. You can't have orchestration by human beings at that point. There's simply not time to respond. You've got to have multiple systems live the whole time. You've got to have things active, ready to take over when stuff goes wrong. At a 99.99, you might get away with something like an N+1 model, where you've got a bunch of live systems and a couple of hot spares that are sat there running, and if one of the live ones goes wrong, you commission one of the hot spares and you're up and running quickly enough. But you're certainly in a world where you're going to have some form of distributed system. You've got multiple computers, you've got multiple things ready to go, ability to deploy on the fly, ability to spot the errors automatically and recover from them automatically.
You get some interesting cultural challenges there. We had one customer where we were deploying an N+1 solution for them for that sort of level of SLA. And they said, but when we're showing customers around our data center, how do we tell them which is their encoder? And it's, well, you don't, because there isn't a their encoder, because as soon as there's a their encoder, when that one dies,
what do you do?
What do you do? It's going to have to move somewhere else. And in order to have it move, a running job move from one server that's just died to another server and have that happen in the course of a fraction of a second, or maybe a second or two, ain't no human being involved in that, at which point the whole notion of this piece of infrastructure is delivering this part of my server just doesn't make sense anymore. And I kid you not, what we ended up having to do for them was we came up with this concept of preferred encoder, that if things were all normal and we had lots and lots of green lights everywhere, then this would be the BBC's encoder, and you could show them around your data center and go, it's that one. They had a label maker and everything.
Yep, yep. We suggested they just stuck the labels on, but that wasn't enough. They actually really wanted it to be real. At 5 nines, you've got to have multiple live systems. You've got to have A/B systems running the whole time. You've really got no choice. It's almost impossible, again, depending on where your SLA is measured, but if you assume you're down at a sort of daily level, the reality is you've got 0.86 of a second to respond. And that's not just to respond, that's to detect and respond. So you've got to spot that something's gone wrong, fix it, and have the end service back up and running before your 0.86 of a seconds is up. That's very little time to do anything, particularly on wide area networks and so on. You know, you've got ping times measured in 100 odd milliseconds. You've only got 860 milliseconds to do it all. That's not long. So you really need A/B systems. You've got to have multiple systems live delivering the service the whole time. This all leads you on to a bit of a catch-22, and this is where lots of things go wrong. We saw this an awful lot in banks. You'd go into a bank and you'd say, show me your systems diagram, and they'd get out this big sheet of A3, and you just think, I'm never going to give you any money, because how that works is beyond me. Resilience requires distributed systems. You need multiple computers doing jobs all the time. You need management and control planes for those systems. Distributed systems are complicated, there's no doubt about that. It's hard to write a simple distributed system. Complexity leads to poor resilience. The more complex something is, more chance there is it's going to break. When it breaks, harder it is to understand why it broke so that you can stop that happening in the future. That's a bit of a catch-22. They go round and round the loop. You sit there engineering to solve your resilience problem, and while you're doing that, what you're doing is you're making your chain longer and longer, and chain is as strong as your weakest link. You're making your chain worse. So you spend a lot of engineering dollars building resilience, and what you're actually doing is making the system worse than it was in the first place.
Again, going back to the banking world, we had big banks, and they would go, oh, well, we'll store our database in here, and we'd go, well, that's not a great idea having it in one place. And they go, don't worry, the NAS that's running on is all fiber, it costs us 7.8 million quid, it's just fine. And then it would go down, and the 2 engineers in the world who actually knew how to configure it were both on holiday, and blah, 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 blah. And actually, the amount of downtime that was caused by the high availability systems was, you'd have been better off with the orchestration by human being.
We had certain customers that ran things like SQL Server clusters. This is rolling back 20 odd years, so things have matured a bit, being fair. But by far and away, the biggest source of downtime was the cluster going wrong, rather than anything else actually happening. And that's not the cluster going wrong because something else had happened. It's just the cluster deciding now's not a good day to die, or I'm just going to fall over in a big heap. Why distributed systems get complicated? They sort of tend, without an awful lot of planning, they tend to get exponentially harder. You tend to have lots of systems talking to lots of other systems, and as you add in new bits, lots of people start talking to them, and your level of communication between all the various parts of your distributed system goes up potentially exponentially. The Kool-Aid is all microservices and service buses and so on and so forth, and they're all great. There's nothing wrong with any of them, but they are so easy to abuse, it's untrue. A quote from a guy who's creating Erlang: if you take a monolithic application and port it to microservices, chances are what you've now got is a monolithic application that has to do with net splits. You've probably not helped your world, you've probably made it worse. You've ticked a few buzzword boxes, but you've not actually made your system better. You need a good ground-up architecture to make sure that a distributed system stays maintainable, stays understandable, frankly stays simple. Simpler it stays, the better. As soon as it starts getting hard to understand how the thing works and how data's getting from A to B and how you're controlling and managing that, chances are you're actually causing yourself problems now rather than solving them. And that's a hard thing to do. That takes a lot of time to understand where you've gone too far and what's necessary and what isn't.
It's also not something that retrofits at all well.
No, it really doesn't. Yeah. No. How do you break the loop? Independence is one of the key ways to try and break the loop. Independent systems don't add complexity. If you've got one system doing a job and another system doing a job and they don't talk to each other, you can treat them as 2 totally independent things, and they're much easier to reason about them, much easier to reason about how they interact with each other because they don't. The more isolated you can make the parts of your world, the easier it is to then reason about how they're going to respond in the face of an error. So keeping A chains and B chains as separate as possible, ideally perfectly separate, is a goal. You can't always get there. Ultimately, they're probably sharing a source, for example. That's pretty common. You'll get quite a lot of customers that want to update config and hit go and have that go to both A and B systems. That's pretty common because customers don't want to deal with 2 sets of configuration or 3 sets of configuration. Every time you do something that impacts all of your systems at the same time, you've introduced a risk point. because if that something goes wrong, you potentially have got a cascading failure where you start taking out your whole world. And you spend a lot of engineering dollars putting together A and B systems, and A and B go down at the same time because someone sent in some bad configuration.
You hit them with the same hammer.
You hit them with the same hammer, yeah. You'll also get systems where the A and the B chain communicate with each other for doing things like timestamp synchronization. And again, you then run a risk that something bad happening on one can then pollute the other. So the more you can isolate them, the better. You can't always get perfection. Customers have requirements, and sometimes those requirements mean you have to talk to each other. But the more you can limit that, the better.
That bottom point is super, super important as well with the it all starts at the player. In order to talk about high availability strategies, actually, kind of the first thing you have to do is say, well, what devices am I targeting? Are they segment-oriented? You know, is it going to be Dash or HLS or one of the sort of segment-type protocols, or are they inherently stream-based, something like WebRTC or how you feed old-fashioned TVs and stuff like that, very inherently stream-based. And the way you go about trying to deliver high availability into those two environments is actually quite different. So a really, really important first question to ask is, what can the player do? How can I support stuff? Because at that point, in most cases, you can get to a position where I'm failing over from an A system to a B system, and my consumer literally hasn't lost a single frame of video. But that does require certain capabilities of the player.
Which leads me nicely onto this picture. We were struggling for the rainbow icon. It's meant to be nice and happy. It needs a unicorn.
That bottom one was a suggested architecture from a real customer of ours.
Yeah.
We didn't implement it, I hasten to add.
So at the top, we've got what we think would be a near-perfect system. You can't always do that. For a start, it's got two sources, which means you've got separate streams straight away. So, there's issues with it anyway. The key is the player at the end. The player has to be able to handle switching from one content server to another whilst it's live. If the player can't do that, then you can't offer a totally seamless system. Because if your content server dies that your player is talking to, and the player can't transition without interruption, then you're hosed.
And by your content server, that could be CDN, Edge Cache, or whatever. Yeah. Unless you have some ability to go from a node I used to be talking to some other node, then if that node you were talking to goes down, so are you.
So if you're on some sort of stream-based protocol, an RTMP protocol or whatever, that makes that quite hard. Because you're having to shut down one session, open up a new session, that all takes time, and you need to be up on the new session and get the correct next frame, which with GOPS and so on might be interesting to know. With a segmented-based delivery, HLS and Dash, that's actually quite a lot easier. And a lot of the players in HLS and Dash will manage that. Not all of them, and some of them do better than others. The best one we've found in our playing around is Radiant, which can manage, I think it can go from an A chain to a B chain and back to an A chain, but it's never managed to go back to the B chain again when we've tested. Lots of others will go from A to B, but then won't go back to A. There's a fair few that won't even manage the first step, even though the manifests and so on claim they should be able to. So your player is the key. Understand what your player is doing, understand what that can deliver to your customer, understand what constraints that puts on what you then need to give to the player. Once you know that, then reverse your system back out of that. And the more isolated you can keep your chains, the better. And I say the one customer came along and said, well, we want everything to talk to everything such that if any one bit of the system goes wrong, everything else in the system can carry on. So that's the bottom picture. If the encoder goes wrong on the A chain, we want the A chain's packager to pick up the output from the B chain's encoder so that it can carry on working so that the A chain, in some sense, is still alive. And it just introduces so many crossover points and so many places for that system to go wrong. And at the end of the day, you still need the player to be able to handle it.
You're solving the same problem n times, and you're squaring your complexity.
We ended up with an implementation for them that only had this crossover. We didn't have these. They weren't adding anything. This helped a bit because some of their devices were stream-based, and failing between the two cloud edges was a challenge for them. So by having that one crossover right near the end, you could try and keep the A chain up right at the edge of the A chain, even if the rest of the A chain had fallen over, such that any players talking to the A chain didn't see a discontinuity. The closer you can get to the top one, the better.
If we had more time, those little red circles with clocks in them are super important.
Yes, they really are.
But we probably don't have enough time. But the ability to sort of create circumstances where you can make consistent distributed decisions across multiple data centers and so on, all has to do, you were talking about it in your session first thing this morning about consistent views of time and being able to come up with consistent segmentation boundary decisions without sharing common state or minimizing the amount of common state.
So your challenge on the very top one is making sure that the HLS segment 10 is the same HLS segment 10 on both chains, even though they're not talking to each other. They need the same PTSs, they need the same DTSs, they need to start on the same iframe.
And that increasingly is deliverable. That's,
that
5 years ago,
is
that was hard, but it's getting there now.
In any one of those chains, having the two chains gives you resilience. If one chain goes wrong, you have another chain you can switch to. You set up your player properly so that it's able to do the transition from one to the other. So you have a route to handle what happens when something goes wrong. You don't want things to go wrong. Much as the strategy of let's make everything work and throw lots of dollars at it is a failed strategy, you still don't want it to go wrong unnecessarily. How do you do that? Do you do it by trying to make your software bulletproof? No, you don't. You do it quite the opposite. You assume everything's going to go wrong. You embrace the fact that things will fail. You develop your systems with that in mind. So, stuff will go wrong. You can't avoid it. And too many people try. You see lots and lots and lots of code where you're just checking error codes all the time. And if you stare at the code, you actually see that like 70% of the code is just handling errors. Call this API. If the result code is good, do this. If it's good, do this. If it's bad, do this. If it's bad, do this. You lose the flow, you lose what you're doing, you lose all the value to your customer. Your customer only cares about the good bit. Embrace the good bit, handle failure totally differently. Handle failure by understanding if this bit does fail and I throw it in the bin, what's the consequence? Because ultimately you can't avoid that happening. It might go in the bin because the power might go. So just accept that that can happen, understand what's impacted by that, solve that problem instead. That's actually a much easier problem to solve. It's not what anyone's taught when they're taught to program first time. It's certainly not what I was taught at college.
And it's a problem you have to solve anyway.
Exactly.
I don't care what software is running on a server. If I turn it off, it ain't running anymore. So
you've got to handle that. So if you recognize that and handle that problem and do all of your error handling with that mindset, you'll actually find that a lot of your code shrinks significantly because you start dealing with the success case and not worrying so much about the error case. Depending on what language you're in, you're going to have to do something in the error case. Otherwise, bad things are going to happen. But it's a very different approach to writing the code. And then how you handle those errors becomes much more manageable. So yes, embrace it. Focus on how you recover from errors rather than how you prevent them. Focus on what impact an outage has and how widespread that is. And again, it comes back to isolation. Make sure your chains are isolated. Make sure the bits in the chains are isolated. If an encoder goes down, try and make sure that when that comes back up again, the packager doesn't care. Try and let the packager carry on running so that your failure doesn't cascade along your system. Make it crash would be the next level up, which is actually design in your system the fact that it's going to go wrong every now and then. That stops you getting lazy. That gives you tests for free. We do this all the time. Most of our systems have got chaos monkeys built into them. We don't tend to run them on the live systems because we don't, frankly, want to anger the gods. But we absolutely run them in QA and dev all the time. So we'll be sat there on our dev systems, writing code, doing a piece of function, and periodically the system will just go wrong for random reasons because our chaos monkey just says, nah, it's time for that to die. And the system needs to handle that. Netflix, fairly famously, I believe, do all of this on their live systems. I believe on Netflix's live infrastructure, they do just randomly turn servers off because it stops their devs getting lazy. Netflix are very much on the embrace the fact that it's going to go wrong, make sure you handle it. So I believe on their live systems, stuff does just get turned off randomly.
I think a fundamental difference between what Netflix are trying to do and what we're trying to do is they're an on-demand type player, at which point
it's
moving something to a different, if I have a live stream and I turn off the encoder, I might recover in half a GOP or something, but it's still going to have some kind of impact into what we're doing. So a less appropriate choice for live, but a totally 100% appropriate choice for live quality control. Unless
Absolutely.
you have your quality verification system having things go wrong the whole time, you have no idea how well you're going to cope with things going wrong. So make them go wrong.
Things like introspection is crucial. You need to know what your system's doing so that when it goes wrong, you can diagnose that and understand what happened and put in mitigation against it in the future if it's something that needs to be fixed. It may be something you can't fix, in which case you just need to understand it happened and report on it.
Dom, I don't know, we're probably coming up to the end of our allotted time. I don't know how much.
Yeah, what we're going to do is we're going to basically shake out my presentation after Thierry's. So we are a couple of minutes over. I don't know if there's going to be any questions, but we should really
We are nearly
wind
there.
up.
I'll skip through the last 2 slides quite quickly. There's a trade-off. Resiliency and latency, do this. Everybody wants low latency. It's what everybody wants because it really matters that much that you're 10 milliseconds above the guy next door. Everybody wants super resilient systems. That's a problem. You can't easily have both. Well, I say easily, just to keep anybody happy here that thinks you can. You can't have both. Live is only live once. You don't have any time to fix live once live's gone. So if you want a highly resilient system, what you need to do is introduce some latency to give yourself time to recover. If you want a super low latency system, you will get errors should things happen. So if you sit there on a WebRTC phone call and there's some packet loss, you'll see the video degrade. There's no choice. There's no time to resend the packets because the ability to resend packets implies there's latency somewhere. So trade-off. You can't have both. We like the Dilbert, but I won't read it. How do we do it? We've been doing this for a long time. We also use an environment called Erlang, which is fabulous for doing this sort of stuff. In particular, it embraces that let it crash approach. So if you want to see systems built with that let it crash in mind, reading some Erlang docs would be a good place to start, or come chat with us. I'll skip over the rest of that. And there's a picture of some of our introspection. That's the sort of stuff we can pull out of live systems on the fly, just for free, pretty much. So we're probably over, but according to our talk clock, I've got 15 seconds left. Any questions? No? Right. We'll be around all afternoon and all evening, so if anyone does have any questions that we can't fit in now, come and grab us.
I will take one question from the floor. It won't be from me because that's unfair.
Oh, go on, Dom.
No, Charles at the front. Here we go.
Now, when you talk about high availability, if you had, talking about, say, physical failure, such as a fiber break, sometimes, it's easy to trace because it's always there. But there is other type of failures we've been talking about, and that is network congestion, and it's caused by things like video traffic or type of traffic,
So
where the peak to average ratio can vary significantly.
Yeah. Yep.
And then it's transient.
Yep.
Before you even go to look what's happening, it's no longer there.
Yep.
And then it happens every so often, a couple of hours, it just happens and messes up the quality of experience. What are your thoughts about how to deal with this kind of failure?
And so at that point, that's why that sort of picture is so important. It's your ability to introspect, to see actual behavior, both in real time of this is what my system is doing right now and how it's behaving, and actually every bit as importantly, and this is what it was looking like 10 minutes ago, and this is what it looked like on average over the last 3 weeks. Because at that point, you can start to take proactive decisions that, while this might look like a great network route for my traffic to be taking out to my CDN for the next... It essentially comes down to economics at that point. If you,
it's a trade-off there with economics and latency. You could go for something like a Zixi protocol, like we were talking about earlier. That will introduce a degree of latency, but it will then give you retry. So if you do get network congestion, you've got chances of still getting the data through. You can drop your bit rate. That's the cheaper way of getting more bandwidth.
So again, one of the things that actually we do, NASDAQ do about 35,000 live events a year with us. And the encoder that's sat, basically there's a kind of packaged up encoder that we provided for them where they plug the camera or the mixing desk into one side. We've done a number of things to sort of minimize complexity there. It used to be that they had a sort of off-the-shelf encoder and it required a trained engineer to go and set it up and have all the right different parameters and so on and so forth and set up network addresses and so on. There is one box on this encoder, which is what's the event ID. And they type in the event ID, it goes off to the cloud, and it says, okay, this is event ID XYZ, it's for Citibank or whatever, therefore it's at this quality, and I'm expecting to have this kind of bit rate. It uses actually not Zixi or SRT, but our own reliable delivery protocol called GRIT. It pushes that out to 2 different locations, one in Europe, one in the States, or one in the States, one in Japan, depending on where the event itself is. And it monitors feedback on the quality of that connection all the time, and will dynamically reduce bandwidth in order to get it through. And in fact, just as importantly, so the use case for them is financial fair disclosure. Somebody's making a share earnings announcement that might impact their share price. The last thing they want is for somebody to come along and go, well, I would have bought £100,000 worth of those shares, but I was disadvantaged because I'm not a professional investor, I wasn't allowed to have it. And so what we do there, there was a comment earlier about live events. You're told it's 50 meg available, and actually by the time everyone's on their phone, it's actually about 2.5 if you're lucky. What we do there as an absolute fallback is we make a phone call into the event, and we mix it in with a slate going, the video will be coming shortly, but here's the audio, because actually they'll have the slides in advance, and so those will, the player, they've still got the slides, they've got the audio from the presenter, they just don't have the head and shoulders shot of the presenter. So, what is it, what value is it you're trying to protect, and then exactly work around the network issues, and there, that allows us to leverage a totally independent network, because that's coming over the PSTN network rather than an IP network. And somehow or other, the cavalry has to get through.
Right, I'm going to have to stop you there, guys. I have to, round of applause to Steve and Adrian. So we have Terry coming up. You've got a presentation up there. I work with these two guys, and I remember I have to not ask them questions because they just blow my mind every day. Right, Terry, have you got your